Welcome back to Fat Mama Physics. This is, I think, episode 5 of this series of topic D1 gravitational field series. In the last couple videos, we went over gravitational potential energy, some examples, gravitational potential. Gravitational potential, we didn't really talk about the conceptual portion of that. It was just the definition so that we have something to work with today when we talk about equipotential lines. In these two videos featuring equipotential lines, you will see two mascots, our Lulu Pig and Shen, who is our amazing singer, featured in some of my one parody video so far. And they will be, you will see them when I show them, you about the contour lines and what they look like and how they're related to gravitational potential lines, or gravity potential and gravitational field lines. So starting with gravitational field lines, just a few things before we begin. Before we talk about equipotential lines, I want to quickly just touch back on gravitational field lines, which you should have seen earlier in the circular motion unit when we talked about Newton's universal law of gravitation and therefore gravitational lines. There is a couple of diagrams that I just want to go over a concept. When we talked about gravitational field lines, imagine here, this is Earth, okay? And we know that the gravitational field strength varies as you move away from the center of the Earth. As you go off into outer space, you might expect something like this, okay, where the gravitational field lines, in terms of the vectors, point towards the center of your point mass. One thing that is interesting here is that you'll notice that as you get closer to the center of the Earth, the distance between the field lines gets smaller. So showing the fact that the density of these lines per cross-sectional area increases. And as the density of these field lines grow, it shows that the gravitational field increases as you go towards the center of the Earth, which is dictated by what you've seen earlier. For the equation for the gravitational field strength shows a inverse square relationship. So we can write this here as the density of the gravitational field lines increase per cross-sectional area, the gravitational field strength increases. And because the gravitational field strength increases, or the density of these field lines increase per cross-sectional area technical unit, it also means that the gravitational field is not uniform, meaning not constant. And that is a new word I'd like to introduce us to, where a certain area where the gravitational field magnitude and direction is the same. So you won't expect that if you go away from the surface of the Earth. On the other hand, closer to the surface of the area, where there's not too much change in the distance away from the center of the Earth, you'll notice that the spacing between these field lines is about the same. So therefore, the gravitational field is relatively constant. And the new word we learned is uniform. Specifically near the surface of the Earth, we use 9.8 meters per second squared towards the center of the Earth. So this is where we do have a uniform gravitational field when it's close to the surface of the Earth. Now you might be wondering, why do we talk about gravitational field in the first place? Because really we transitioned from gravitational potential, and we want to talk about what that actually looks like. We want to conceptualize that. So to do that, we need to introduce something called the equipotential line. An equipotential line uses part of the gravitational line definition. Just a recap on gravitational potential. Gravitational potential is the work done per unit mass in moving something from infinity to some point in space. Or if you're talking about gravitational potential difference, then it's between two different points in space. Again, the per unit mass comes into play. An equipotential line is a line where the gravitational potential is the same anywhere along this line. And to add on to this, these equipotential lines should also be perpendicular 90-degree angle to your gravitational field lines. So this is where this other diagram here is why that's there. So if this was Earth, for example, then the green lines are your gravitational field lines, and those concentric rings are then your equipotential lines. And I'm just going to stop after 2 lines because it'll get really messy. But if you take a look at those circles, they are 90 or should be 90 degrees to your gravitational field lines. You might also notice that these concentric rings are denser when they're closer to the center of the Earth and further apart as you go away. If you guessed it has something to do with the inverse formula or the inverse relationship between the distance from the center of the Earth, then yes, you're onto something. But that's something I won't show us until a little bit later. For now, I want to really dive into what are equipotential lines and what are gravitational potential. What is gravitational potential and what's the significance and what does it all mean and what's the context, etc. To do that, we are going to bring back some geo. So if you're taking geo, hopefully you've seen something like this. It's a contour map or a topographical map. Maybe you've seen one of these. So thank your geo teacher for this, if you know this well. So if you did if you've seen a contour map, then you should very well know that these lines that you see here that are in red, they're called contour lines. These contour lines represent the height of elevation above sea level. If you go hiking, we see this a lot, and we actually, when we go hiking, we plan out, which path to take depending on elevation, especially with younger kids. And this lovely diagram, I think I got from Cognity, but it really shows the 2D drawing and what that looks like in 3D space. The reason why I'm introducing this, is I like us to see gravitational potential as an analogy to these contour lines. And I'm gonna have the mascots Lulu Pig and Shen take us to a new destination to show us the significance and explain how these are all related together to gravitational potential. Contour mapping can be seen in all sorts of applications. In fact, I just found this in one of our board games, Dune Imperial Uprising, and in fact we 3D printed this. It was pretty easy and surprisingly amount of detail a 3D printer can put into these contour maps. You can see all the different gradients here, different colors, the blends. We just printed it for tactile purposes for the board game. But anyways, that belongs right there. And in the background, you have our mascots for this unit. We have Shen and Lulu Pig. Here I built this using my kid's Duplo. Pardon for the colors, trying to find different, just a color scheme that's going to work for the amount of pieces that I have. So the contour lines are similar to your equipotential lines, in which every single line represents, or everywhere along this line represents the same gravitational potential. So here yellow, or here I have the base, assuming that sea level, and like contour maps, if you go up to the next level, that's say 100 meters, and then you have 200 meters, which is your red, then 300 meters, which is your blue, 400 meters, your green, and then I have some repeated colors. What was it? 0, 100, 200, 300, 400, 500, and then 600 meters above sea level. So notice one thing that's unique about these contour lines is that every single line is of an equal interval. So it goes up by 100 meters. It doesn't just go by 100 and suddenly it goes up to 300 or suddenly 1,000. So the interval between each line is the same. And that goes the same thing with equipotential lines. So let's say the base we have is, this is not a great example of equipotential line, but let's say at the top we have is 0 joules per kilogram. Then here we might have, say, negative 100 joules per kilogram, negative 200 200 joules per kilogram, negative 300, negative 400, negative 500, negative 600 joules per kilogram. So every single line represents the same interval between for that scalar measurement. Let's say we can also use the contour lines for this particular analogy. Let's say we have fat, chubby Lulu pig. Yeah, Lulu pig wants to, Lulu pig is going to walk along the yellow contour line, which is in the context of topographical maps. That would be your 100 meters above sea level, for example. Go behind. Okay, Lulu pig comes back to original spot. Has not made any changes to the height. Here is your chance to guess how much work was done by Lulu pig in staying on the same contour line. And if you guess 0 work done, you're absolutely correct. Okay, because there was no change in height, no change in gravitational potential energy, and therefore the work done was 0, assuming Lulu pig did not accelerate in that process. Another question or conceptual question to ask is, let's say Lulu pig decides Lulu pig wants to scale the mountain. So Lulu pig goes all the way to the top of the mountain, very top. Ugh. Hello, can you see me? And that comes all the way back down to the same line, or actually let's change the position to somewhere over here, also the yellow contour line. In that case, what would be the work done by Lulu pig? Would it be positive, negative, 0, or do we not have enough information? Here's a chance to make your educated guess. And if you said that the work done by Lulu pig is 0, assuming that there was no changes in any other form of energy, you are correct. However, you might have been thinking, well, Lulu pig has to go up the mountain. That's going to take a lot of work, right? Well, technically, yes, Lulu pig could do that. So Lulu pig does gain all that gravitational potential energy. But don't forget, if Lulu pig just decides to slide down or convert all of that gravitational potential energy into kinetic, going back to where Lulu pig started off, then that change in energy, the gain and the losses cancel out. And so the net change in energy is still 0. So all of that potential energy gets converted into kinetic, back to where Lulu pig started off. You might have thought that Lulu pig needed to, in order to climb the mountain, needs to have some amount of kinetic energy in order to convert that into gravitational potential energy. So in that case, Lulu pig kind of has to do some work, right? But don't forget, as Lulu pig goes all the way to the top of that mountain, Lulu pig's gained all that gravitational potential energy and can now convert that gravitational potential energy back into the kinetic energy that Lulu pig might have had in the beginning. So overall, the net change in energy is still the same. So the key message is that as long as you start and end up on the same equipotential line in our analogy, which is a contour line, then the work done or the change in energy or change in gravitational potential energy is 0. Bye. Say bye, Shen. Bye. It looks like Shen didn't do anything. It was all Lulu pig. Anyway, so coming back, hopefully you have a little bit better understanding, especially with moving between those contour lines. We're going to translate some of those things that we got from that piece, what Lulu pig and Shen showed us, onto our notes here. First of all, the line 8. So here I just want us to cross out this because this is from a different picture that I forgot to cross out earlier. We will talk about the steepness of the slope and how that relates to the distance between the contour lines in the next video. So we're just focusing on definition and what it is first. So hopefully one of the key things you got out of the video is that these contour lines are similar to your gravitational potential. Gravitational potential, or in your words, your equipotential lines, meaning the higher you go, the greater your gravitational potential. Also in the video, the video talked a little bit about what it means to stay on the line what it means to move away from the line and come back to the line. So it doesn't matter what you do in between, as long as you come back to the same line, the net change in energy is 0, therefore the work done is 0. And don't forget, whatever you're moving is called a test mass, and again, the potential difference language comes back. If that's 0, then there's no work done. The video also mentioned a little bit about what the lines mean, or what in terms of contour maps. We know that the lines represent a measurement of meters or height, but that's not the same thing with equipotential lines. We know that the unit for gravitational potential is joules per kilogram. So if we have to, and in the video I mentioned how a topographical map of, say, a mountain is not going to really look like a real equipotential line map of space. To look at equipotential lines in action from a point mass, we kind of have to go back to one of our previous videos about equipotential energy. And if we see how the graph is below the x-axis and shows an inverse relation, or this is inverse relationship, your gravitational potential is going to look pretty much the same. In fact, if you go into your notes and you go to a little bit further, this one here where it talks about gravitation inside the Earth, this page here, there is an example what it looks like here. So it's the same thing. The graph looks like an inverse graph. So I'm just going to draw that here to emanate that. Starting off with the x-axis, this is a distance value from the center of the mass. And then because this is below the x-axis, I'm going to draw this arrow downwards. This is Vg for gravitational potential, measured in units of joules per kilogram. And the line of the inverse graph kind of looks like this. So if we start off from the top, we might have 0 joules per kilogram. And then we might have over here negative 100. Notice it's going below 0. And I'm just going to be careful here of equal distance of separation of these numbers. Okay, so going all the way down to negative 400. And assuming these are all equally spaced. One thing that's mentioned in the video is that anytime you see a contour line or an equipotential line, just like your elevation map, every line typically represents the same interval. So if you're going up by 100 meters or going up by 10 meters here in the diagram above, equipotential lines tend to do the same thing. So if I had to draw, if this curve represents like a well, if you imagine a well, we use gravity, we use potential wells in physics language a lot. So if you imagine this is an actual well, the equipotential line are at these points that I've labeled, negative 100, negative 200, negative 300, negative 400. So if you take that, this is kind of like if you imagine this is kind of like a circle, or if you imagine it from like a 3D drawing perspective. Okay, so the circle kind of wraps around that well, representing the same equipotential space. So this doesn't quite look like a mountain or a hill you're expecting in a topographical map. And of course, everywhere along this line represents the same gravitational potential with a beautiful inverse curve between distance of separation and gravitational potential. Now, remember I mentioned how in this diagram up here, how the contour lines tend to start very close together and get further and separate further out as you move away from the point mass. You can kind of see it visually here, and I tried my best to put the lines kind of at the correct spaces apart from each other on this this line graph that I have. So in the very beginning, when you go to negative 400 to negative 300, the distance of separation is very small. And then as you go further away, it gets a little bit larger and even larger and so forth. So that the equipotential lines get further apart as you move further from the point mass. I can also show us this mathematically as well as visually. I'm just rearranging this equation here. So big G, big M over VG, just to show the relationship between the R's and separation. And also I dropped the negative sign just to reduce clutter on the board here. So at this point, let's start off here. This is the R is equal to big G, big M over 400. Over here, this is big G, big M over 300. Then here, this is big G, big M over 200. And this is big G, big M over 100. Now, what you could do is you can subtract these two numbers to find the difference between them. But I'm just going to tell that to you because I'm not trying to make you do math. I just want to show you the difference, how it's increasing as you go further away. So if you add big G, big M over 1,200, it gets you to the next number. And I'll quickly do the first one just to show you I'm not lying. So we're adding fractions. You know, if you want to make a common denominator, remember? Great night, Matt. So then as you make them into the common denominator, you get 3 big G, big M over 1,200 plus big G, big M over 1,200 again. So you get 3 plus 1, and that gives you a total of 4 big G, big M's over 1,200. And if you take 1,200 divided by 4, that is 300. Which is exactly big G, big M over 300 over here. Okay, so I'm just going to get rid of that because I need that space, because I'm going to just tell you, because I did the math for you, what these next numbers are going to be. So big G, big M over 300 plus big G, big M over 600 gets you to the next radius of separation, big G, big M over 200. And then this one over here, the last one is big G, big M over 200, which gives you finally to big G, big M over 100. And so you'll notice that these numbers here, this is a very small number, then it gets slightly bigger, and then bigger and bigger. And so the separation gets bigger and bigger and bigger. So visually, bam, mathematically, bam. So this is why you see these concentric circles get larger. Okay. Anyhow, that's just a little detail. But the key is just to see the inverse relationship and to see that gravitational potential lines are like contour lines. So that if you're trying to move something up a contour line, like if you're trying to scale a mountain, it of course gets very hard the higher, the further up you go and go. And same thing, if you're trying to move up this potential well, if you're trying to move, away from your object, from your point mass, you need to add more and more energy the further away you go up that well. Which means that if you stay on that line, if you stay on that contour line, if you stay at that sea level, at the same sea level, you are not changing your elevation. You do not need to put in energy to change your gravitational potential energy, and therefore no work needs to be done. Otherwise, I think I've extended the stay for this video. I'll see you next time on the next video, because then we will take gravitational potential. And then this is where it gets really interesting, how it ties very nicely with gravitational field. Otherwise, Fat Mama Physics signing out. See you in the next video.